really want to experience old types up to the third floor of the faculty offices and going and bathroom up there. It's like the worst. It's seriously, like whenever anybody makes a mistake of going in there and opens the door, it just rolls down the hallway. Like, oh my god! Half the professors keep their doors closed all the time, so they smell it. All right, so what we're going to do is we're going to continue our study of, now the class has begun, and I've got this recorded for posterity here. We're going to continue our study of linear maps. I want to remind you that a linear map has the form, so we say T is linear. E to W, if T of X plus Y is equal to T of X plus T of Y. X are a lot of times we use the notation TX plus TY. They mean the same thing. It just means use X or Y as the input for T, and T of CX is equal to C TX. Okay. Yep.
I have a little question about this.
Sure.
It seems like we talk about like additivity and homogeneity a lot, and is that just because like we only want to work in line?
It's because basically the idea is that when we talk about linear algebra, the idea of, yeah, so linear is part of it, but the other part is we want the linear maps take vector spaces to vector spaces. So the range, we're going to prove today that the range of a linear map is a vector space. So the idea is these are the exact conditions that we want so that if we feed a vector space in, we get a vector space out the other side.
Okay, and so linear mappings are always going to be between vector spaces?
Always.
And not, would there be one that's like in between an individual vector, or is that just like?
No, I mean, you apply a linear map to individual vectors, but like you could, the only vector space consisting of a single vector is the zero vector, right? So a linear map that was only defined on a single vector would basically be, well, take in zero and put zero out the other side, right? So yeah, I mean, but these things, if it seems like a just so definition, it kind of is, because we set these things, this is not an accident that this is the conditions we choose. We choose these conditions precisely so that we can manipulate the vectors either in the domain or in the range, and that there is vector space structure on both sides, in the domain and the range. Okay. Now, this space, L of VW, is the vector space of bounded, that is the vector space of linear maps VW. It's assuming here that D is finite dimensional. So this is just a notation that means every map that is a linear map on from a particular vector space into another. Okay? And this turns out to be a vector space because if you have two functions, you can add them together and get a new function. Right? That's basically the idea. By adding two things in here together, you get a new function out the other side. So the operations are so this thing, you have S and T are elements in this space. Then S plus T is in the space. And also C times S will be in the space as well. Taking two linear functions and adding them gets you a linear function. Taking a linear function and multiplying it by a scalar gets you a linear function. This is what we mean by this as being a vector space, is with these operations. Also, 0 is a linear operator. It's not a very interesting one, but 0 is a linear operator, right? Turn everything into 0 is a linear operation. Yeah. Yeah, I mean, technically, if you want to prove this, you actually have to show that all the properties here hold exactly what you want. But if you think about the set of all functions, remember the set of all functions from some set to another set is a space, right? So you can actually, there's ways you can sort of trick that definition up to just use the subspace definition. I'm not going to prove this because it's actually really easy to show all these things hold. But if you actually want to show this as a vector space without reference to some overarching space, you do need to argue that this satisfies all 8 properties. It's not hard to do. So if you want to do it, you're welcome to. If you don't want to, then just accept that this thing has the closure properties we want. Okay, now the thing about this particular vector space that's weird is that often we can actually get a notion of multiplication for vectors in here. And that's unusual for a vector space, right? In most vector spaces, you can't multiply things. You guys might think, oh, but we had a dot product and a cross product in, say, on all vector spaces that, all RNs have a dot product. And if we're in R3, we have a cross product. But the idea is that we want to be able to work generally on vector spaces, 1. And 2, the dot product is not really a good product because you take in 2 vectors and you spit a scalar out the other side. The idea here is that if I have an operator T that takes a space W, a vector space W into a vector space U into W, and an S that takes U into, how do I want to set this up? This is going to go to V, and then this will go from V to W. Then this thing is an element of the linear operators that start in V and end in W. The idea is if you have the vector space U, you hit it with T, that spits you out into V, you hit it with S, that puts you out into W. So we can define multiplication by composition. So we define ST applied to some vector U to be equal to S composed with T applied to U. So if this makes sense, if we have things mapping into the right spaces, so if T goes from U to V and S goes from V to W, I can freely compose these things because it makes sense to do so. And if I can compose them, that actually defines a multiplication of these operators, right? Which is weird because multiplying vectors is weird. And for those of you that have seen a little bit of abstract algebra, yep. No. No. So there's a couple things we want to say about this multiplication, right? So the analogy I want you to have in mind is multiplying matrices here. Generally with matrices, what would it mean to divide by a matrix? Multiply by the inverse of a matrix. Does every matrix have an inverse? The answer is no, right? So generally, just because I can multiply doesn't mean I can divide. There's no natural notion of division that comes along with this necessarily, right? The second thing is, with matrices, is it true just for matrices? No. So in general, this multiplication, that means this multiplication is an example of a non-commutative multiplication. So this is a non-commutative multiplication. Generally, ST and TS can't be reversed even when it makes sense to do so. Okay. And that's related to the idea that matrix multiplication can't be reversed. So that's not true, and not every element has an inverse. Not every S in, say, LBW has an inverse. Those of you that have seen some higher level abstract algebra, this is an example of something called an algebra. So it's a vector space a vector space with a multiplication is an example of an object called an algebra, or ring if you like, another sort of structure you may have seen in other classes. Okay. And what you're talking about where you can actually divide is called division algebra. And this is not. Yep.
So you can multiply linear maps, but not vector spaces?
Yeah. So the maps, so like you can imagine here. So what do I mean? What I mean is, suppose that we had a vector space V. So V is a vector space. And I talk about L of V. That's all functions. This is the set of linear maps from V, right? So things that map the vector space back to itself. So this will always make sense in that context, right? S composed with T, that's perfectly okay. That takes V to V to V. T goes from V and spits out a V vector, and then S eats a V vector and spits out another V vector. So that will always be fine. This multiplication makes sense as functions that live, that eat the vectors in the vector space. Okay, so you can multiply the functions. When I say map, you should think function, right? A linear map is a function. So the functions can be multiplied because I can think about multiplication as composition. Yep.
Would an example of this map be like a scaling or rotation?
Yeah, or I could give you even like imagine that your vector space B is equal to differentiable functions. Functions that you could take derivatives of, that's a perfectly good vector space. So how about I let my function S be equal to S of a function F that lives inside the space of differentiable functions. Maybe I take x squared and I multiply it by f of x. Right? That's a linear operation because if I did S of f plus g, well, x squared times f plus g is x squared f plus x squared g, which is S of f plus S of g, right? I can do that. I can. This is a perfectly good linear function on the vector space of differentiable functions. Another one would be taking the derivative, right? D of f is equal to d by dx of f. That's a linear operation as well. Derivatives are linear. So multiplying a function by x squared is a linear operation. That's a linear map. Taking the derivative of a function, that's a linear map. So those are examples of the sorts of things like S belongs to, S is an element of this space of functions, right? S is an element of the linear operators on V. We assume like to say C1 differential. And D is another differential or is another linear map in the same family. And the notion here is, the reason I keep saying non-commutative is that if you computed SD of a function f, what you're saying is, let's just what we're saying is take x squared and multiply it by df dx. Do df dx first, and then multiply it by x squared, right? That's what that composition would be. ds of f would say take d by dx of x squared f of x. Are those operations the same? Well, no, the chain rule, or sorry, the product rule is going to say that this is 2xf plus x squared df dx. And those are not the same map. This is an illustration that you can't just reverse the order when you're multiplying maps like this, right? SD gets you one thing, ds gets you a different thing. They're both linear. The product makes sense, but the products aren't the same if you go in either direction. All right. Okay, and this product, the fact that this product exists, this is why this vector space is interesting, right? This vector space is interesting because it's not just a regular vector space. It's a vector space where you have this weird multiplication idea stuck to it too. Okay, yep. Yes. Right, so the idea is, if you're in here, if you're in the linear operators on V and you compose with another one, you stay a linear map, right? Like if you take a linear map and you compose it with another linear map, that's actually a good exercise to check that that's the case. So you can check actually that if S is in L of V, is in L of V, and S composed with D is in L of V. Not a hard exercise to check that that's the case. And that would mean checking those two conditions, that S composed with T of X plus Y is equal to S composed with T of X plus S composed with T of Y, and also that S composed with T of CX is equal to C times S composed with T of X. So if you can check those two conditions, you will have shown the map is linear. Okay. Okay, this is the sort of this is not like anything that probably showed up in 206, if you guys remember your 206. In 206, you did everything in terms of matrices. Here we're stepping back and doing it abstractly. The idea to try to study things that kind of act like matrices, but in a kind of an abstract way, instead of locking ourselves down to matrices. Are there questions about this before we go on? Okay. Okay, so at least if you believe Axler, L of VW is interesting, as he says it is. I mean, it really is, but he says it, so you got to believe it. So what we're going to do is we're going to define something called the fundamental subspaces. So we're going to look at fundamental subspaces. These are ideas that you almost certainly have seen before. So for a linear operator, sorry, for a linear map, sorry, I'm saying operator, I'm not trying to confuse anybody. For a linear map, T, there are two fundamental subspaces. One lives in the domain of T, one lives in the range of T, or the codomain of T. So we're going to study the null space of T. That's one of them. And that lives in the domain. And we're going to look at the range of T. And that lives in the codomain. Okay, before I go on, the word codomain is something you may not have seen before. Is there any, can anybody tell me what a codomain is?
It's the space in which the range lives in, I guess you could say.
Why do we make a distinction between the range and the codomain?
We'll say you have a function that takes like a real number to a real number. That function might not output all real numbers, but your codomain is the real numbers. So it's not, the range of the function might not be the entire codomain.
And the reason that we want to do that is because we're studying lots of functions all at the same time. So if I'm studying lots of functions all at the same time, it may not be the case that, like, if the outputs are always in this vector space, each individual function may not cover all of the output, or the output of each individual function might not be all of W, but each function in this family has outputs that are in W. So this space is called the domain. This space is called the codomain.
Is range always a vector space?
Huh. That's like the very next theorem in my notes is to prove that the range. Actually, I guess we're going to do range after we prove that the null space is a vector space. We'll prove that the range is a vector space as well.
Okay, so you could always define like the range instead of the codomain. Like,
Well, I mean, so the reason that you don't want to do that is because you really want it to be the case that the range of these things is not always going to be the entire vector space. It might be a subspace of it.
but you could always define a vector space that would fill the entirety of, right? It's always.
Yeah, I mean, then composition starts to not make any sense, right? Because if you compose functions and your range isn't all of W, then you can't chain it up with another one of these. So it matters to say, like in theory, all of these compositions make sense, but the way that the range acts as a member of this vector space, as a subspace of this, actually matters a lot. So we don't want to just necessarily cut down to a subspace.
Mm-hmm.
Yep.
B to W,
Yeah.
B to U, I mean, you use a subset of W, and that set of functions, a subset of
Okay. Can you rephrase?
that. So right,
Just say it again.
set of all functions from B to U,
So you have L from G to U.
use a subspace of W,
U is a subspace of W.
and that set on the left, the subset of the one.
You could think about these functions as living inside these, yeah. All right, so I'm going to define the null space. The null space T and L, P, and W is the collection of vectors that T sends to 0. Everything T destroys. So an example of a null space here. If you could probably tell me. Suppose my vector space is P5. So 5-dimensional or less polynomials. That's my vector space. And I define the operator D to be differentiation. What's the null space of differentiation here? What vectors in the space of degree 5 or less polynomials is the differential operator set to nothing? Constants, right? D, but the derivative of a constant is 0. Is the derivative of anything else equal to 0 or just the constants? Just the constants. So this operator, so like this linear map differentiation turns constants into 0. And so the null space of differentiation is everything that looks like P of X is equal to C, where C is a constant. So the null space of differentiation is the set of vectors that get destroyed, turned into nothing by the map. Okay. You guys, I'm going to give you a 206 idea here. I'll leave this definition up. So here's an idea that you probably did a bunch in 206 was, suppose that you have T of x1, x2, x3 equal to z1 plus 2z2 plus 3, or sorry, this is supposed to be here, z1 plus 2z2 plus 3z3. That's a linear map. So the null space of T, the set of all vectors, z1, z2, and z3, that this thing turns to 0, is equal to every vector, so that z1 plus 2z2, all vectors in the domain have the property that z1 plus 2z2 plus 3z3 is 0. Everything that you fed in that produced a 0 out the other side. But that could actually be described pretty easily. I mean, you guys have done a ton of this in 206. Writing down a map like this, figuring out the null space as an equation, and then saying, oh, that means if z1 plus 2z2 plus 3z3 is equal to 0, then that means that z1 is equal to minus 2z2 minus 3z3, which means the set of vectors that look like minus 2z2 minus 3z3, z2, z3, those are the sort of things that if I put them into the equation, 0 would come out, which is z2 times minus 2, 1, 0 plus z3 times minus 3, 0, 1, which you then write as the span of minus 2, 1, 0, minus 3, 0, 1. And I guarantee you, if you took 206, you did a million examples of this particular exercise, right? Find a basis for the null space was basically this exercise over and over and over again. Okay. Null spaces live. So what sort of vectors does T take in? What is the vector space that T is acting on? Or F3. So I guess we don't know, right? So say F3. And what is coming out the other end? F. F1. Okay, so notice the null space lives in the domain of a function. Null space is vectors in the domain. It's important to remember. Null space is in the domain. The vectors that we got out were span of vectors in F3. Those are elements in the domain of the operator. Okay, so null space is attached to, well, actually, let's do this first. Here's a theorem. This is a fun one. Null space of T is a subspace of B. Null space of T lives in the domain. So null space of T, if it's going to be a subspace, it has to be a subspace of the input space. How do I prove something is a subspace?
Additive.
Subspace, additive closure closed under addition, closed under scalar multiplication, includes 0, right? Okay, so is 0 in the null space of T? Is 0 in the null space of T? Well, let's see, I don't know, is T of 0 equal to 0? And the answer is, yeah, we proved that like 2 times ago, that like linear maps, I mean, we're asking about like why the rules are set up the way they are. It's to force things like this to happen. T of 0 is equal to 0, so that means that 0 is in the null space of T. How are we going to show that it's closed under addition? Well, let's let E and W be elements of the null space of T. We want to show that V plus W is in the null space of T, but to be in the null space of T means T sends you to nothing. So really what we want to show is that T of V plus W is equal to 0. That's what we really want. So the way you do that is like this. Well, if V and W are in the null space of T, then this must be true. 0 must be equal to TV plus TW. Because V is in the null space of T, and W is in the null space of T. But T is linear. I guess we're done. So this line holds because T is linear.
Can you explain the first equal signs? again?
Sure. Here, I'll be slightly more clear about it. 0 is definitely equal to 0 plus 0. Remember, what we're trying to show is that this is true, right? But if T is linear, then that means really what we're trying to show is that this is true. But I know that's true because V and W are both in the null space, right? This is what it means to be in the null space, is that T sends you to 0. So I'm going to carefully uncancel a 0. This 0 I'm going to pretend is T of V, and this 0 is T of W, and I'm going to use the linearity of T to yank it out and do that. And since T sends V plus W to 0, since T of V plus W is equal to 0, that means that V plus W is in the null space of T. This line? Okay, so what's the definition of T being a linear function? T is linear. It's really when we say is in L V W, what we mean is for all U and V, T of V plus V is equal to T of V plus TV. That's true for every U and V if we have a linear function. And also we're going to use this, T of CU is equal to CTU. To be linear means you automatically can pull T across sums like this and you can factor scalars out. So that's what we did right here, was we used linearity. It's basically just repeating the fact that we set these rules up so that would have forced this to be the case, right? I mean, this is why we chose these rules, is so this argument works. Yep.
So the null space will be
Oh, you reading ahead of the book or something? Yeah. In fact, yes, actually. So just like if you remember that theorem where you've got some idea of what's happening here, you're destroying information. The very next thing we're going to do is attach this to the idea of injectivity, right? That the null space actually measures when a function is one-to-one and when a function is not one-to-one. It's actually precisely the definition, or not the definition, it's the main condition that we use to check injectivity of this map, or one-to-oneness, right? So yes, it's precisely the very next thing we're going to talk about. Okay, so I need to check one more condition. So 0 is in the null space. The null space is closed under addition. So I started with 2 elements in the null space and showed that our sum is in there. I also need to let C be an element of the field, and let's let B be an element of the null space of T. And then I'm going to notice certainly the case that 0 is equal to C times T of V. T of V is equal to 0, right? So that's true. 0 is equal to C times 0, but T of V is equal to 0 because V was in the null space. And then linearity lets me pull the C inside. like that. And that means T sends C of V equal to 0. It seems kind of artificial, but basically what I'm doing is I was starting with this line and working this direction and seeing if I got 0 out.
So you started with, why did you start on the C without that?
Well, because like if you were trying, so suppose what you want to show is that T of CV is equal to 0, because that's what would mean that CV is in the null space, right? So pretend you didn't know that was true. What would you do? You would start by writing, like, I don't know, maybe if I'm lucky, I'll write this down and maybe I can manipulate this expression until 0 falls out of it. Well, what can I do? T of CV, I don't have a lot of moves I can make, right? Somehow I have to use the fact that this is true. So I want to try to use the fact that I can do that. If I ever see a TV, I can write a 0 down. Well, I have one move I can make, which is that. T is linear, I can get the C out. But B is in the null space of T. So this is C times 0, which is the 0 vector. This is sort of the forward direction of the same argument. These arguments are the same. So that means that CV is in the null space. That means that null T is a subspace. But I want you to be really careful when you write what it's a subspace of. From this point in the class, when you write something as a subspace, make sure you tell me where it's a subspace. Null T is a subspace of V. It's important that we hammer into our heads that null spaces live in the domain of functions. Okay, now we're going to get to injectivity. All right, here's the definition. A function T that takes V to W called injective or one-to-one if TU equals TV implies that U is equal to V. Now you guys may have learned other conditions for one-to-oneness, like things like horizontal line test. That's not going to work here because we can't visualize these maps for general linear spaces, right? One-to-oneness basically says that if the outputs were the same, the inputs had to be the same. Distinct outputs come from unique inputs. Okay, so this algebraic condition is the usual way that we check this. If the outputs were the same, the inputs had to be the same. So thematically, or not thematically, in different language, to say that a function is one-to-one is to say something like each distinct output comes a unique input. If the outputs were the same, the inputs had to be the same. Is that okay? All right, so here's the big theorem. Jump up and prove it if you want. I'd be happy. All right. Oh, that's an open offer, by the way. Anybody ever wants to get up here and prove here, you're welcome to. Like that, dead serious. No one ever takes me up on this. But if you guys ever want to come in here and practice what it's like to sit in front of a classroom and explain to an audience of math students like how proof works, you are absolutely welcome to ask me. I'll give you 15 or 20 minutes to come up here and give a presentation on it. I won't force you. If T is in L of VW, then T is injective if and only if the null space of T just the 0 vector. So that completely characterizes when a function is one-to-one. One-to-one functions are functions that if they basically going to make outputs unique, this is essentially saying, well, you just have to check that it puts 0, that it's one-to-one if and only if it's one-to-one at 0.
What do you mean by that?
So I mean, like one-to-one, injective or one-to-one would mean you'd have to check every single output and make sure that the inputs don't, that if you have the same output, that you always have to have the same inputs to do it. And you have to check that for every single possible output. What this theorem is saying is you could do that, or you could just look at what happens to zero. If the only vector that t sends to zero is the zero vector, then automatically everything else was one-to-one as well. Right? If zero in the range can only come from zero in the domain, then every other output was unique also. Yep.
The TU equals TB implies that U will be that type of the same.
No. Okay. No. I mean, if U equals V, definitely T is equal to V. That's automatic. Like I said, here's something that's a 2, and here's another thing that's a 2. What does F do to it? Well, F of 2 is definitely going to be equal to F of 2, right? So this is a much stronger thing to say. Right. If you guys haven't thought about this in a while, the idea is like if you have something like a parabola. Parabola is not one-to-one. I mean, the way that you probably learned it was, oh, you do this horizontal line test, and since the horizontal line test crosses the function twice, the function is not one-to-one, so you can't invert it. What's actually going on here is that the same output, say the output 1, happens when you apply F to 1, which is 1, but also F of -1 is equal to 1. So it can't be the same output did not force the inputs to be the same. Right, so that's actually, so the algebra here is sort of reflecting something like a horizontal line test. The outputs were the same, but the inputs were different, which means 2 different inputs produce the same output, and that's why one-to-one this failed. Right, so this is intended to capture this idea, but in an algebraic way. Yep.
And the output is like the range.
Yeah, we haven't defined range yet, but yes, the outputs are the range. So the range of a function is going to turn out to be all the possible outputs. You feed in all the u's, whatever the tu's are. That whole set is the range of the function. Yes. Yep.
Why do you call it this if then?
If and only if.
Like that, if T is in the middle, is that just kind of.
Well, if you're at, so the definition of injective was for general functions, any function from B to U, right? This requires, this is only true if I have a linear function. So linear functions have that special spreading across some property, right? This in general is badly not true. It's only true for linear functions, right? So this part of this condition is super important in this theorem, right? This is not true of general functions, but it is true if the function is linear. So a linear function has the property that injectivity is equivalent to the null space being just the zero vector. But for the broader family of functions, that's not true. And the theorems are going to start becoming structured like this, where there's a hypothesis, and then the conclusion is another logical statement, right? If you are a linear function, then this equivalence holds, is how you're supposed to read this. So this block holding is supposed to imply that that block holds.
When you write null T, that means like a set of.
Well, now not anymore because we just proved null space is a subspace, but yes. So whenever I write null T, you should think it's the subspace of everything in the domain of T that has a property that T sends it to 0. That's what these is one of these definitions that, again, I talk about, you're 90 years old and your great grandkids come over. This is one of these that you got to have in your head, right? The null space is the set of vectors that T sends to 0. That just got to be in there.
So when you apply T onto these vectors, it gives 0.
It's everything that T spits a 0 on.
So in this case,
The only vector that T turns into 0 is the 0 vector. Nothing else.
Okay.
Nothing else. Right. So question, is it the case, is the derivative operator one-to-one? Is that injective? If I take derivatives of functions, is that a one-to-one operator? And the answer is no. The derivative of x squared plus 2 is 2x. And the derivative of x squared plus 3 is 2x. So if I'm looking at the 2x over here, if this is a one-to-one function, I could tell you exactly which input gave me the 2x. But look, 2 different inputs gave me the same output. So this is not a one-to-one function.
What if like writing something?
Someone's riding down.
Okay.
What is it?
It's the dude like coolly riding down on his one wheel on one, like standing on one foot.
To be fair, he did look pretty cool.
I mean, it's got glowing lights on it, man. It's got ground effects. Anyway, so yeah, so generally these things are not one-to-one because again, we can think like, this is not one-to-one and I can check the outputs to see, oh, look, this output had two different inputs that it came from. But what the theorem says is it would have been enough just to see what got sent to 0. As soon as you say, oh, well, the null space of the derivative operator is equal to all constants. Well, all constants is not just the 0 vector. And so automatically by that theorem, it must mean that this is not a one-to-one function. Does that make sense? Okay. So I'll write this proof out, I guess. Actually, you know what? That proof, I'm going to leave this proof. I want you to read this one. So this theorem, I'm going to assign this. This theorem is instructive, and I want people, if they have questions about it, I want you to ask me about it. So I'm going to assign. I'm not going to walk through this one. I want you to read this proof. And the reason I want you to read it instead of like sitting and watching me do it is because the whole like, oh, I watched somebody do something, so I understand the thing that happens in like I used to do in math classes. And then you go home and try to read it yourself or do something with it. Go, oh my God, I do not understand what's happening. So the ideas that show up in this proof are really important because it's going to involve the definition of what it means to be in the null space, that is turning vectors into 0, and also the definition of injectivity. So you should read that argument and make sure that you understand it, okay? Because the idea of the connection between injectivity and the null space is really important, okay? And that argument, the technique in that argument is going to show up in the homework as well. And then if we come back like tomorrow and there's a bunch of questions about it, I'll walk through the proof, but I don't want to just give the game away. I want you guys to read it, okay? The theme of this is that injectivity, one-to-oneness, is attached to the null space of T. So the null space of T, which is a domain condition, is attached to the injectivity of the function. The other fundamental subspace, what about outputs? This is all about inputs of a function. What about the outputs? That's what we always mentioned, the range. So we can define the range of T. This lives in the codomain. This lives in the codomain. Right? The range of T is an output. It lives in the output space of vectors. So the range of T is everything of the form TV where V is in V. Every possible output. Feed every input into T and look at what came out. That's the range. Yep.
Have you asked us to write these definitions on the test, or you just do the range?
Oh yeah, this is the best. This is absolutely the best way to do it. I say a lot of words because I'm trying to anchor these sort of like axiomatic definitions to the concepts that are attached to them. But this is the definition. Right. The range of an operator is just plug every single thing in the domain and keep track of what came out. Okay, now it may not be surprising to you if I call these things the fundamental subspaces, but it also turns out to be the fact that the range of T is a subspace too. It's a subspace that lives in the codomain. Any guesses as to what functional quality the range is going to be attached to? If surge activity, that's right, that's where we're going with this. So the null space is attached to one-to-oneness. And then range is going to be turned out to attach to onto-ness or surge activity. Okay, but first we have a theorem here. It says range of T is a subspace of W. This is for T in W. All right. As before, it's useful to like take a walk through the proof of this kind of thing. Again, this is not a hard proof, but the idea is we have to check 3 things. 0's in there, it's closed under addition, closed under scalar multiplication. It should not surprise you we're going to be using linearity of T again as our main tool. Is 0 in the range of T? Sure it is, because T of 0 is equal to 0. show something is in the range is to say it came from something in the domain. How about if U and V are in, let's actually go with say, what are some good range letters? How about W and oh, that's gonna be stupid. How about just W1 and W2? And what I want to show is that W1 plus W2 is in the range of T. How would I do that? How am I going to show that this vector is in the range?
You apply T to it.
What do I have to find? If I want to show something in the range of a function, what do I need to find? I need the vector it comes from, right? I need to find a vector that if I plug it into T, this falls out the other side. So I need the input. I'm saying if I want to say this is in the range, you better be able to show me what the input is that makes this the output. I have an idea though. I bet I can use the vectors that make these to build the vector that makes that. This is how a range argument works. This is the reason I skipped the previous group, because I want you guys to see this. If W1 and W2 are in the range of T, then there exists a U1 and a U2 in V in the domain, so that TU1 is equal to W1 and TU2 is equal to W2. That's what it means to be in the range, right? To be in the range means you came from somewhere. There must have been an input element that produced you if you're in the range. How could we use that? Oh, how about I just, okay, what if I looked at W1 plus W2? Well, that would be TU1 plus TU2. If only I could find a vector that if I apply T to it, W1 plus W2 falls out. Oh, but look. Linearity says that's true, right? T is linear, so I can just factor it out. And there you go. That input right there is the input that produces W1, W2 is the output. So that means that W1 plus W2 is in the range of T. To show something is in the range, I must exhibit the element in the domain that it came from. So I've used here the fact that, again, the idea is that these arguments are very similar. Range arguments always involve a step like this, where you say, oh, that's in the range, so I can write it as T times something from the domain. And then these are the vectors that we use. Okay, so null space arguments always are going to use the fact that we have that they get sent to 0. Range arguments are always going to involve asserting that they came from some vector over in the domain. Right? Right. You can use the same argument to show that this thing is closed under scalar multiplication as well, which means that the range is a subspace. So I would say similarly, C T of U1 is equal to T of C U1. And on this side, this is equal to C of W1. And that would show that it's closed under scalar multiplication. All right. So range of T is a subspace in the codomain. What we did not get to today, but we'll get to next time is I will reiterate the conclusion of this argument. And what we're going to do is we're going to show that the range of T dictates whether or not a function is onto or surjective. So null space tells you if a function is injective, range tells you if a function is surjective. And then if you put those together, if you're surjective and you're injective, then you're invertible, right? Or I'm sorry, I shouldn't say that. I meant bijective, bijective. Sorry, bijective, bijective. Let's not talk about invertibility yet. All right, I'll see you guys next time.
I need to talk about.
Yes.